This is Chapter 2, Part A, Chemistry Comes Alive. So you may be wondering, why do I have to study chemistry in a biology class? Well, the body is made up of many chemicals, and individual cellular function is going to be a product of various chemical reactions and chemical changes within the cell. So chemistry underlies virtually all of our physiological reactions in the body. So things like movement, digestion, pumping of the heart, and nervous system function. So in order to really have a good understanding of biology, you need to have a decent understanding of chemistry. And then if you go even further, if you want to learn more about chemistry, then you need to know about physics. So biology is essentially chemistry in action. And then if we look further, chemistry really is just physics in action. So the three of these are kind of inherently linked in the sciences. So there's two types of chemistry that we'll look at in this chapter. So this section will look at basic chemistry, and next section we'll look at biochemistry. So basic chemistry is just how the elements and the atoms interact to make different molecules, so types of chemical bonds and different properties of the elements and the atoms. Biochemistry or organic chemistry is the chemistry of biological molecules. So molecules that make up living things and are produced by living things. So matter is anything that has mass and occupies space. So anything that we can see, smell, and or feel. Right? So things that we can detect with our senses or other measurements. So when we talk about weight, we're talking about the mass of the matter plus the effects of gravity, right? So your weight on Earth would be different than your weight on the moon, where the gravity is different. So remember from elementary school, there are three states of matter. So we have solids, liquids, and gases. So solid states of matter have a definite shape and volume. Right? So think of an ice cube. Right? So solid water has a definite shape. It's not going to change its shape. It's not pliable. And the volume's not going to change. With liquids, you have changeable shape, but a definite volume. So you may only have 8 ounces of water in the glass, but you can slosh it around in there and it'll change its shape. Right? It'll conform to whatever container you put the liquid into. Gases are able to change shape and volume. So we can compress the container of a gas and pressurize it, which would change its shape and its volume. So as we increase the heat to these different states of matter, so again, think of water. So you have ice, and then we add heat. It's going to melt into liquid water. We add more heat. It will eventually evaporate into the gaseous state. Energy is the capacity to do work, or another way to say to put matter into motion. So there are two possible forms of energy. So we have kinetic energy, which is energy of action or motion, and potential energy, which is an inactive stored form of energy. So energy can be transformed from potential to kinetic and back again. So a good example of this is a roller coaster. So as the roller coaster gets to the top of the hill, the potential energy increases. When the roller coaster goes down the hill, it then converts the potential energy into kinetic energy. There are four main forms of energy. So chemical energy is stored in the chemical bonds of different molecules. So this is ATP, the primary energy molecule of the cell. So this powers a lot of cellular functions, and it does this by releasing energy in this third phosphate bond here. So when this bond is broken, we're able to harness this energy to use for other purposes. Electrical energy results from movement of charged particles or electrons around a circuit. Mechanical energy is physical movement, so directly involved in moving matter. So it's kind of that kinetic, physical, mechanical energy. And then finally, radiant or electromagnetic energy. So this type of energy travels in waves. When we talk about wavelengths, has to do with the energy of the wave. So some examples would be things like heat, the visible light spectrum, ultraviolet light, X-rays, gamma rays, microwaves. All of these are part of that electromagnetic energy spectrum. These different types of energies may be converted from one form to another. So an example would be when you turn on a lamp, right, we're converting the electrical energy from the electricity or from a battery into light energy. So this energy conversion, though, is not 100% efficient. So the second law of thermodynamics just says that basically every time you convert from one form of energy to another, some of that energy is going to be lost as heat, which is partly unusable energy. So this is why the light bulb would get hot, right, when you turn the lamp on. So when you drive your car, we're converting chemical energy in the fuel into mechanical energy to make the car move, right? But a lot of that energy is going to be burned off as heat. So this is why as soon as you stop your car, you can't just pop the hood and touch the engine. It's going to be very hot. All matter is composed of elements. So elements are substances that cannot be broken down into simpler substances by any ordinary chemical methods. So these are kind of the building blocks for everything that we know of. So all of the known elements. So out of all of these elements, there are only 4 that make up about 96% of the entire body. So these 4 elements that make up 96% of the body are carbon, oxygen, hydrogen, and nitrogen, or CHON. So carbon, hydrogen, oxygen, and nitrogen. 9 other elements make up about 3.9%, and then some other trace elements and minerals. So things like iron, sodium, potassium. All elements are made up of atoms, which are the unique building blocks for that element. So they're the building blocks of the elements, and the elements are the building blocks of everything else in matter. These are the smallest particle of an element that still have the properties of that element. So these atoms, the structure of the atoms, or what give each element its particular physical and chemical properties and determine its position on the periodic table. Carbon atom is going to have a different number and amount of these subatomic particles than, say, a lithium atom. So this is one way we can distinguish between the different atoms and elements. When reading the periodic table of elements, we look for the atomic symbol. The atomic symbol is a 1 or 2 letter chemical shorthand for each element. Carbon is C, O would be oxygen, nitrogen is N. So a lot of atomic symbols will have the first letter of the word as its atomic symbol. Some symbols come from Latin names, though, so they might not always be as intuitive on which element it is based on the atomic symbol. So Na is for sodium, K is for potassium, iron is Fe. Right? So there's several examples where the Latin names are used instead for the atomic symbols. Atoms are composed of 3 subatomic particles. So we have protons that are going to carry a positive charge. So pro for positive. And they're going to carry a weight of 1 mass unit. So we say each proton just weighs 1 mass unit. Neutrons are neutral, so they have no electrical charge. And they also weigh 1 mass unit. Electrons on the outer surface carry a negative charge. And they are considered to have a weight of 0 just because they are so tiny compared to the protons and the neutrons. So looking at the structure of an atom, the number of the positively charged protons is balanced by the number of negative electrons. So this way they kind of cancel each other out. So the atom would be electrically neutral. The protons and neutrons are found in the nucleus, or kind of the core of the atom, and the electrons orbit around the outside. So kind of like a planetary model, where the nucleus, the protons and neutrons would be the sun, and the electrons are the planets that kind of orbit around that nucleus. We can identify different elements based on the numbers of these subatomic particles. So hydrogen has 1 proton and 1 electron, whereas helium has 2 protons, 2 neutrons, and 2 electrons. Lithium has 3 protons, and so on and so forth. So these are unique characteristics for these atoms. So identifying facts about an element include its atomic number, the mass number, any isotopes, and the atomic weight. The atomic number is just the number of protons in the nucleus. Right? So it's typically going to be shown on top of the atomic symbol. So for carbon, right, we have 6 protons in carbon. So the atomic number is 6. The mass number is the sum of protons and neutrons. Remember, both protons and neutrons are considered to have a mass of 1. Right? So if we add 6 plus 6, our atomic mass is 12. So this is the total mass of the atom. And again, remember, the electrons are so tiny, their weight is considered 0. Isotopes are structural variations of the same element. So sometimes an atom can contain the same number of protons, but differ in how many neutrons it has. So the atomic numbers would be the same because our protons are not changing, but the mass number, the sum of the two, would be different. So we're adding on extra neutrons. So stable carbon has 6 protons and 6 neutrons. Right? So its mass is 12. Right? Carbon-13 has 1 extra neutron, so its mass would be 13. Right? Same thing, carbon-14, we have 2 extra neutrons, right? So its mass number would be 14. Some of these isotopes are unstable. So radioisotopes are isotopes that will decompose to more stable forms. So as the isotope decays, it's giving off these subatomic particles. And as they expel these extra neutrons and subatomic particles, they're releasing little bits of energy referred to as radioactivity. So we're able to detect and measure various degrees of radioactivity with scanners and technology. So it's commonly used in nuclear medicine and diagnostic. So looking at combining matter, molecules and compounds. So far we've just been talking about atoms and elements kind of individually, but in reality, most atoms aren't going to be isolated by themselves. They're going to chemically combine and socialize with other atoms and form molecules and more complex structures like compounds. So a molecule is just a general term for 2 or more atoms that are bonded together. Right? So it could be 2 atoms of the same type or different. So if we have 2 atoms of oxygen bonded together, it's a molecule of oxygen. Right here we have a molecule of chlorine. Right? Whereas a compound is 2 or more different kinds of atoms bonded together. So if it's a compound molecule, it's a bit more complex. Right? So these on this bottom row would be compounds. So water is a compound, right? Carbon dioxide. This is a chemical formula for glucose, which is a compound. Right? So again, if it's a molecule with just one type of atom, like these here, it's just called a molecule. So one way you could think of it is that all compounds are molecules, but not all molecules are compounds. Just like atoms usually will interact with other atoms, most matter will exist as mixture and interact with other types of matter. So most matter exists as a mixture where 2 or more components are physically intermixed. Right? So we're not talking about chemical mixing or chemical bonding, just kind of a physical mixing. So they're physically in the same space. Right? So there's 3 basic types of mixtures. A solution is when the solute particles are very tiny. They do not settle or scatter out light. So this just means that it dissolves completely. So you're not able to tell that there's anything in the solvent or in the water, right? So an example would be salt water or mineral water. So just looking at it, right, it looks clear. It looks like there's nothing in there because it's been completely dissolved and the solutes are very, very tiny, so you're not able to detect them. A colloid mixture is when the solute particles are larger and they do scatter light. So we won't have a completely clear solution. Like in this example, we would have kind of a cloudier or opaqueness to the mixture. So examples would be like Jello, milk, paint. So they are mixtures, right? But they're not completely clear. Suspensions are where the solute particles are very large and they easily settle out and they may scatter light. So a good example of a suspension mixture is blood, right? So blood is composed of plasma fluid and blood cells, right? So if we look at just a tube of blood, right? So the light has been scattered, right? Light has been obscured, so it's not a clear solution. And if we were to spin the tube in a centrifuge, the gravity of spinning would cause the heavy red blood cells to settle at the bottom of the tube. So we are able to settle out these large particles and separate them in the mixture. So the difference between mixtures and compounds. So three main differences. Unlike compounds, mixtures do not involve chemical bonding. Right? So mixtures are just a physical, occupying the same physical space, essentially. There's no chemical bonding occurring. So this means that mixtures can be separated by physical means. So we can strain out the solutes or filter them out. Whereas compounds can only be separated by breaking the chemical bond. So you need some type of chemical reaction to separate those components. So in this example, we have element X, element Y. So in a mixture, right, they're just kind of occupying the same space, whereas compounds, they are chemically attached and bonded to one another. So chemical bonds are the energy relationships between the electrons of reacting atoms. So electrons are the key players here in our chemical reactions and chemical bonding. So electrons are going to determine whether or not a chemical reaction will take place, and if so, what type of chemical bond is formed. So there's different types of bonds, different types of interactions these electrons and atoms can have. So they could maybe share electrons, or one atom could donate electrons to another atom. The outermost level or shell of the electrons is called the valence shell. So electrons in the valence shell, or this outermost shell, are the ones that are going to interact with other atoms, and form chemical bonds. So because they're on the outside, essentially when you form a chemical bond, the atoms have to kind of bump into each other. So when they bump into each other, these outermost electrons are what's going to interact. The electrons in the deeper shells are kind of insulated and protected from that outer valence shell. The octet rule is the rule of 8. The rule of all chemical bonding is that atoms want to have 8. 8 is the magic number. So we want 8 electrons in the valence shell. There's a couple of exceptions, like with smaller atoms like hydrogen, helium, because they only have one shell. The first shell only holds 2 electrons, so they're satisfied with 2. They don't need 8. But all other atoms want to have 8 electrons. So this drive and desire to have 8 electrons is what's forcing these chemical reactions to occur. So some atoms already have a full valence shell. They already have 8 electrons. So these are considered inert and not chemically reactive. So these are also referred to as the noble gases. And they're found in column 18 on the periodic table. But because they already have a full valence shell, they're pretty content. So they don't have a need to interact and cooperate with other atoms to get 8 electrons, because they already have 8. So these are the more kind of antisocial atoms. But most atoms don't have the luxury of having a full valence shell. So atoms will interact by gaining, losing, or sharing electrons and forming chemical bonds with other atoms. So that way they can both achieve that stability of 8 electrons in the valence shell. So there's 3 types of chemical bonds: ionic bonds, in which electrons are transferred; covalent bonds, electrons are shared; and hydrogen bonds. So ionic bonds are where atoms lose or gain electrons. So electrons are transferred from one ion or one atom to another. So once they lose or gain an electron, they're going to take on a charge, right? Because remember, protons and electrons usually balance each other out, so the atoms are neutral. So when you lose or gain an electron, you're losing or gaining that negative charge or negativity. So now our protons do not equal the number of electrons, so there's kind of an imbalance there now. The atom that loses an electron is called the cation. So it has a positive charge, right? Because it's giving away an electron, it's giving away some of its negativity. The anion is going to gain an electron, and it will carry a negative charge, right? Because it's taking on a new electron, it's also taking on that negative charge that goes along with it. So one way you can remember the cation, right, is an ion with a positive charge. So another example, sodium and chlorine, right, to make sodium chloride, basic table salt, right? So sodium has one valence electron, right, in its outer shell. So if we just get rid of this one, the second shell already has 8, right? So the shells add as we fill. So we get rid of this one, we give it to chlorine. Chlorine only has 7, so it only needs 1. So these two work out a deal, right? So now they both have 8 and they're happy, right? But now they've got a charge. And remember, opposites attract. So these opposite charges, positive and negative, are going to be drawn toward one another. So it's kind of like a magnetic attraction at this point that's holding these atoms together and forming the chemical bond. Covalent bonds are formed by the sharing of 2 or more of those valence shell electrons. So covalent bonds, they are cooperating, right, to reach that full 8 valence shell. So this allows each of the atoms to have a full valence shell at least part of the time. So they're sharing. So I get the electron for a little bit, and then you can have it for a little bit, and we'll both, get our time with a full shell. Right? So everybody's happy. So this example, to make a molecule of oxygen, right, so O2. So oxygen has 6 valence electrons. Right? So each one needs 2 to reach 8. So they share 2 electrons together, right? And now they have 8. So now we have 1, 2, 3, 4, 5, 6, 7, 8. So this would form a double bond. So covalent bonds are able to form in various formations. So we could have 4 single covalent bonds. We could have a double bond or a triple bond, right, where we share 3 electron pairs. There's 2 different types of covalent bonds depending on the sharing of the electrons. So a nonpolar covalent bond results from an equal sharing of the electrons between the different atoms. So this would result in a balanced, kind of symmetrical molecule, right, nonpolar molecule. So an example here, right, it's an uncharged, right? Hydrogen has the same charge on both nuclei. The electrons spend the same amount of time near each nucleus. So as the electrons are orbiting, right, they spend equal amounts of time around each atom. Polar covalent bonds result from an unequal sharing of electrons. So one atom in the molecule is going to kind of hog the electrons more than the other ones. So this results in our electrically polar molecule. So polar just means that you have 2 opposite ends. So you have like a north pole and a south pole. Well, we have a negative pole and a positive pole. So atoms have different electron attracting abilities, leading to this unequal sharing. So just meaning that some atoms, maybe larger atoms, have a stronger pull on the electrons than others. So water is the classic example of a polar molecule. So it's H2O, right? So we have a oxygen atom and 2 hydrogen atoms. So the oxygen atom is much larger than the hydrogen atoms. So the electrons are going to spend more time near the oxygen atom, right? So, and not as much time near the hydrogens. So because all of the negative electrons spend most of their time up here, this would be the slightly negative end of the molecule, right? They spend less time here, so this is the slightly positive end. Hydrogen bonds are a bit different than ionic or covalent bonds because there's no electron interaction involved. So we said chemical bonds were the result of interactions between electrons of different atoms. Well, hydrogen bonds aren't true chemical bonds in that sense of the word. They are more or better defined as a weak magnetic attraction. So we talked about water being a polar molecule, so it has a positive and a negative pole or end. So just like with the ionic bonds, the opposite charges will attract. So water molecules are attracted to one another by these hydrogen bonds. Right? So we have kind of a weak think magnetic attraction between the negative end of this water molecule and the positive end of this water molecule. So this provides us with surface tension. So how a bug is able to walk on the surface of the water, right? So there's weak bonds holding the water molecules together. But again, they're very weak bonds. It wouldn't take much force at all to break through the surface of the water. Hydrogen bonds can also act as intramolecular bonds and hold other molecules together. So molecules like proteins and DNA. So DNA, the two strands of DNA, are connected by these weak hydrogen bonds. So this is beneficial when we look at DNA replication. So when we replicate and copy DNA, we have to kind of unzip this double helix, and we have to break all of these chemical bonds. If these were covalent or ionic bonds or stronger bonds, it would take more energy, right, to split the strands apart. Right? So this allows us kind of an easy mechanism for DNA replication. Chemical reactions occur when the chemical bonds are formed, rearranged, or broken. So they can be written out as a chemical equation. Chemical equations contain the reactants and the products. So the reactants are kind of the ingredients of the chemical reaction. The products are the final end products, the result of this chemical reactions. So the amounts of the reactants and the products are going to be shown in a balanced equation. So we cannot destroy or create new atoms. We can only rearrange them. So the number of the different atoms will not change, only their arrangement. So we have one carbon here, one carbon here. We have 4 hydrogens here, and we have 4 hydrogens here, right? They've just been rearranged. So one type of chemical reaction we see is a synthesis reaction. So this is where we're synthesizing or making something. So 2 or more molecules combine to form a larger one. So this is an anabolic or a building metabolism. So when we take individual amino acids and we can bond them together to make proteins. So we're synthesizing new molecules, larger molecules. A decomposition reaction would be the opposite. So decomposing, we're breaking down larger molecules into smaller ones. So this is considered a catabolic or breakdown metabolism. Exchange reactions are a combination of synthesis and decomposition reactions. So 2 molecules are going to exchange atoms or groups of atoms. So this involves breaking bonds and forming new bonds. So we're going to break the bonds between A and B and C and D, and then we're going to form new bonds and synthesize AC and BD. The rate of chemical reactions or the speed at which they occur can be affected by things like temperature. So an increase in temperature is going to usually increase the rate of the reaction. So the particles in the mixture or the solution with increased temperatures will move faster, right? And we said chemical bonds, atoms have to essentially bump into one another. So the faster these particles are moving, the more likely they will collide and interact to form the chemical bonds. Concentration of reactants also can increase the rate of a chemical reaction. So again, back to the principle of we have to make the atoms bump into one another. So if you have more atoms or molecules in the same space, it's a higher chance that they will bump into each other and interact. Also, particle size can play a role. So smaller particles usually travel faster. Right? Larger particles move a bit slower, so they would be slower to react. Catalysts are things that can increase the rate of a chemical reaction without actually changing the products of the reaction or becoming part of the reaction itself. So enzymes are what we use for our biological catalysts to help speed up and facilitate our own cells' chemical processes. So essentially how catalysts work. So all chemical reactions require what's called an activation energy. So without a catalyst or without an enzyme, we have to climb all the way up this hill before we can start the reaction. With an enzyme or a catalyst, it just decreases the steepness of the hill. So we don't have to use as much energy to get the ball rolling, right, and to get this reaction completed.